Hello everyone, welcome to our session. My name is Chen Chen, and the topic we'll talk today is breaking theoretical limits, the gap between virtual NICs and physical network cards. Before we start, let me give a brief introduction to our team. We are from code-safe team of LegendSec at Qianxin Group, and mainly focus on the software source code security analysis and binary vulnerability research. We have reported many critical vulnerabilities to companies such as Microsoft, Apple, Google, Cisco, and so on. Additionally, some members have been consistently featured in the Microsoft Global Most Valuable Security Research list. Also, we have presented at conferences like POC, Hacking Boss, and Black Hat before. Here we go now. This talk is broken down into 4 parts. And part 1 will start off by introducing the related stuff about a virtual network interface card. In part 2, we'll dive into the network module of Hyper-V, including its driver architecture, packet transmission flow, as well as the comparison between physical network cards and virtual NICs within Hyper-V environment. In part 3, we'll share some vulnerabilities discovered by breaking the theoretical limits outlined by RFC. Part 4 is a summary of this talk. Start with the introduction. Virtualization technology, which is a crucial component of the cloud, provides the foundational technology for creating and managing virtual sources like virtual servers and virtual networks. In virtual networking, virtual network interface card provides functionality like open vSwitch and communication between adjacent virtual machines. Considering it serves as such a fundamental and low-level infrastructure, it has become an appealing target for virtual machine escape. The following are hardware characteristics of physical network card shown in Windows and Linux platform. Regarding compatibility, when virtualizing network interface cards, some characteristics often need to be simulated and implemented through software, in case that the physical network cards underlying the virtual environment lack support for them. Especially, software support for the following features like UDP segmentation offloader and large center offloader are often required. Among them, USO is to offload the task of segmenting large UDP packets into small fragments from CPU to NIC, while ISO is to offload the task of segmenting large TCP packets into small fragments from CPU to NIC. In other virtualization software such as VMware and QEMU, there have been some vulnerabilities existing in these features before. Common types of virtual network interface cards include E1000, E1000E, VMXNet, VMXNet2, and VMXNet3. Besides those basic functionalities, the primary feature is to provide functionality that have been migrated from CPU to network interface card. As we can see, the tasks such as packet fragmentation, checksum calculation are originally handled by CPU in the past. Nowadays, these tasks are offloaded to hardware interface network card. The behavior is based on a concept from computer architecture. Offload as many computational tasks from the CPU to hardware devices as possible during I/O process, thus improving overall performance. When targeting virtual network interface cards, one common focus is on those functionalities that have been moved from CPU to network interface card, like ISO and USO. Additionally, attention may be given to configuration commands similar to RNDIS. Fuzzing and code review are the 2 typical methods used. Alright, with the general idea of virtualization technology and virtual network interface cards. Let's move on to the next part. In part 2, we will describe our research and findings on the Hyper-V network module. At first, we attempted to use KAFO for fuzzing, but it gave low promising results. Then we switched to the traditional approach, conduct code review on the binary. After lots of analysis, debugging, and testing, it turned out that we were able to send a normal packets which broke the theoretical limits outlined by RFC. The following is a single ICMPv6 packet whose length is 69741. Here, it breaks the 65535 length limitation. Another example of a normal packet is a single AIP packet whose length is only 15, and it breaks the 28 length limitation. By the way, as shown in the picture, actual patterns are added by the operating system. In some cases, this may lead to information disclosure. Compared to the IO port method, using VM bus mapping allows the direct writing of IO port and IO memory command information into the buffer. Then DMA mapping is accomplished through VM bus control. This method generally provides better performance. Apart from Hyper-V, other virtualization software like VMware is also gradually abandoning the traditional IO port method. As mentioned before, the packet from guest is mapped to the host through VM bus. Then VM switch will handle and pass it to the IO protocol stack. From the host's IO protocol stack perspective, there are two different sources of incoming packets. One is the traditional way to read packets from physical link. The other is mapped in through VM bus. As to the former, as packets need to pass through the physical and data link layer, there are limitations on the packet size. In contrast, for the latter, since packets are mapped in through VM bus without passing through the physical and data link layer, they are not subject to length restrictions. Since the same implementation is applied to both cases, while the latter may break the hidden assumptions within the implementation, it may lead to unexpected behavior. We can examine the process of packet transmission in the latter scenario by viewing the code stack. After the packet being mapped in through VM bus, the VM switch module will call RNDIS dev host handle packet message function fast to get the packet from message. Then it will proceed to the protocol processing function registered in the VM switch for NDS module. After a series of filtering, verification, and addressing, the routine will reach VMS VMNIC PVD packet forward function. Then it will invoke the corresponding handler on the protocol stack to send the packet. With a general understanding, let's first recap how to send normal packets from guest to host. After invoking the send service function in application layer, the corresponding packet undergoes various processing and verification routine in the network I/O protocol stack before reaching the netvsp driver. The netvsp driver will convert the packet into a message, then call VM bus send packets function to map it to the host through VM bus. Now here comes the question: how to send a normal packet from guest to host? Based on above routine, it's clear that we can just hook the VM bus send packet function and modify the corresponding message in the netvsp driver. The packet will follow the same flow as described earlier, reaching the host through VM bus, and the subsequent steps will be similar to the previous. Next, let's take a look at the general process that a packet undergoes in VM switch after arriving. In VM switch module, it will first perform initial processing, such as assembling the message into a packet. Subsequently, the packet undergoes the filtering process, involving filter and routing serious functions. The primary purpose of these functions is related to addressing, as the packet may be forwarded to different destinations, such as other virtual machines or different network segments. The filter series function typically refers to filters, forwarders, and monitors provided by Microsoft and Hyper-V Virtual Switch Manager, including Microsoft Windows Filtering Platform, Microsoft Azure VIP Switch Extension, Microsoft NDS Capture, and so on. Following this is the forward series functions, as the packet's destination may be other virtual machines or the internet, each corresponding to different process functions. For example, VMS MP NIC PVD packet forward function is used for forwarding packets to virtual machines. VMS PT NIC PVD packet forwarding function is used for forwarding packets to the internet. And the VMS VM NIC PVD packet forward function is used for forwarding packets to the host itself. In general, VM switch is rather complex, as it acts as a driver for the virtual switch, enabling communication between the virtual machine and the physical network. To understand the VM switch driver, it's essential to mention the NDIS driver. If you have previous knowledge of NDIS stack drivers, you can consider the VM switch driver as the device driver stacked on top of NDIS. The driver stacking behavior relies on a series of function pointers registered by the device driver object. Many of the function pointers in the VM switch driver are registered as protocol handle functions pointers in the NDS driver. Therefore, by taking the VM switch as the large stack driver, it's easier to understand its main routine involved in sending and receiving packets. This can be further confirmed by examining the code of VM switch driver. In the driver entry function, we can see strings for stacked device objects such as VMS VSF and Hyper-V Virtual Switch Extension Filter. Additionally, there are calls to functions like NDIS Register Protocol Driver function and NDISF Register Filter Driver function, supporting that it operates as a stacked driver. After understanding the network virtualization behavior of the VM switch driver, let's take a look at the general process flow of packet in the host. When a packet reaches the NDS driver, it will be forwarded to different protocol handlers based on the type of packet. These handlers may be registered by VM switch, TCP/IP, or other drivers. Once forwarded to the protocol handler, subsequent process is identical, but the initial incoming packet has different resources, and most importantly, packet entering through VM bus are not subject to length constraints. In conclusion, those packets mapped into host through VM bus without going through the physical and data link layer are not subject to length restrictions. At the same time, the same implementation is applied to diverse sources of incoming packets, while the latter may break the hidden assumption within the implementation. In consequence, it may lead to unexpected behavior. From our perspective, it means vulnerability. In the next part, we will share some vulnerabilities we found caused by abnormal packets that break the length constraints outlined by RFC. The first one is CVE 2021-24074, as can be seen from the MSRC Security Advisory. It's a critical vulnerability with the corresponding CVSS 3.1 score of 9.8. The root cause is integer overflow and caused by a single ICMP v6 packet whose length is bigger than 65535. A normal ICMP v6 label advertisement packet containing some ICMP v6 options is shown below. In general, its length can't exceed 65535, but as you may expect, in our scenario, we can break this length limitation. The following is part of code stack related to this vulnerability. As we can see, the control flow, originating from the VM switch module, eventually enters the TCP/IP module. This indirectly confirms the packet processing flow in the host as discussed in part 2. In TCP/IP module, IPv6p handle router advertisement function is responsible for handling the received ICMP v6 advertisement packets. In this function, a while loop will be used to sanity check the options before doing anything permanent at 2. It will first call IPv6p part TLV option functions to pass ICMP v6 option to get its length and type. Then sanity check will be done against this option. If it satisfies, NETIO advanced let buffer will be called as 3 to move the pointer forward to the next option. At 4, variable path length is used to keep track of the path length. The while loop exists normally when all the options have been passed and validated successfully. At this point, the pointer will point to the end of the last ICMP v6 option. Then, NETL retreat let buffer function will be called at 5. Its purpose is to retreat the pointer to the buffer by a specified number of bytes, preparing for subsequent packet processing routine. In normal cases, the value of path length field will be equal to the total length of all passed ICMP v6 options. It's worth noting that the path length variable is a 16-byte unsigned short integer. If we corrupt a single ICMP v6 packet whose length exceeds 65535, we can call integer overflow at 3. Then, when calling NETL retreat let buffer later, the retreat behavior would go wrong, thus messing up a subsequent packet processing routine. The next one is CV 2022-13223. It's an information disclosure vulnerability in Windows Hyper-V. The root cause is out-of-bounds read and caused by a single ARP packet whose length is only 15. A normal ARP packet is shown as follows. In general, its length can't be less than 28 bytes, but again, in our scenario, we can break this length limitation. The following is a part of code stack related to this vulnerability, and the vulnerability located in VMS MBO help create a clone MBO function from VM switch module. In this function, in some cases, the routine will reach 1. Will search for is assigned to variable v12. Then it will be passed to NDS copy from let buffer to let buffer as the third argument as 3. The NDS copy from let buffer to let buffer is used to copy a specified number of bytes from source buffer to destination buffer, and its third argument is exactly the bytes to be copied. Here is 34. Based on our standing, the constant 34 here refers to the minimum length of an IP packet, which includes a 14-byte link header and a 20-byte IP header. If we corrupt a single ARP packet whose length is only 15, then we can cause out-of-bounds read as 3. thus leading to information disclosure. An example is shown as follows. A 15-byte ARP packet is expanded to 34 bytes, resulting in kernel address leakage. The third one is the long point dereference issue caused by a packet with only 8-byte IP header. As of now, it seems that this vulnerability has not been fixed by Microsoft. We reported this vulnerability to Microsoft as early as April 2022 and has multiple communication with them subsequently. However, Microsoft seems to have difficulty reproducing the issue due to inconsistent environments, leading to a delay in fixing this vulnerability. Considering that this vulnerability has not been fixed yet, we prefer not to discuss much details about the vulnerability here. Below is the recorded video demonstration. In this video, we first set up two virtual machines in VMware Workstation, one running Windows Server 2016 and the other running CentOS. And within the Windows Server virtual machine, we create a large virtual machine using Hyper-V. Then we send a crafted packet from the CentOS virtual machine to the Windows Server virtual machine, which is then forwarded to the internal Hyper-V virtual machine. When processing this malformed packet, due to a long point dereference issue in one of the modules in Hyper-V, it eventually leads to a blue screen in the Windows Server virtual machine. Let's play the demonstration video. The last part is a simple summary of this talk. First, we learned that in Hyper-V environments, the virtual network interface card is not totally identical to physical network card. Extra considerations must be taken into account. Otherwise, the hidden assumption within the implementation may be broken. Then, we'll share some vulnerabilities we found, which are caused by abnormal packets that break length limitations. Finally, by utilizing these vulnerabilities as case studies, we hope it serves as a point for code review or fuzzing when targeting virtual network interface cards. Maybe it's also suitable for other virtualization software like VMware, QEMU, and so on. Okay, that's what we shared today. Wish you all have helped. If you have any questions, you can reach us by Twitter or email. Thanks.